Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Welcome back. Problem 5.13. So the statement is assuming that the reaction of the ground is uniformly distributed. Draw the shear and bending moment diagram for the beam AB and determine maximum absolute value of shear and bending moment. So we have this beam AB that is placed on the ground, and this ground is acting a uniformly distributed load on this beam. At point C we have a point load, and at point D we have a point load. So what you have to find is, first you have to find, or you have to draw shear force and bending moment diagram. Then it has been asked to find the maximum absolute value of shear. So V maximum absolute value of shear, and V is maximum absolute value of bending moment. So let's start with the solution. As you can see that beam is exerting the ground is exerting uniformly distributed load. So we will draw the free body diagram. This is the beam, clear, and at point C there is a point load. Similarly at point D there is a point load. This point load is 1.5 kilonewton. Similarly at point C we have 1.5 kilonewton. This is point A and this is point B. This floor is replaced by uniformly distributed load. So I will show it over here. And let this load is W. Clear? The total length of this beam is 1.5 because 0.3, 0.9 plus 0.3 is 1.5. So total length is 1.5 meter. From A to C the distance is 0.3. So from here to this distance is 0.3 meter, and from D to B this distance is again 0.3 meter. Now we will apply equilibrium condition in order to find this W. Okay, so we will apply sum of all forces along y direction must be equal to 0, and taking upward force as positive. So you can see there are three forces. One is this, second one is this, and third one is W acting on this beam. So 1 minus 1.5 because it is downward. Similarly this minus 1.5 is downward, plus this W load, and when this W load is multiplied with the length it will give you the force. So 1.5, which is the length, into this uniformly distributed load over the 1.5 length will give you the force, upward force. Their sum must be equal to 0. So it means that 1.5 W is equal to 3, because minus 1.5 is minus 3, and when you move it toward right side it will be plus 3. So W will be equal to 3 divided by 1.5, which is equal to 2, and the unit will be equal to kilonewton into kilonewton per meter. So we have this W is equal to 2 kilonewton per meter. Now we will move toward finding the bending shear force and bending moment at each section. So first we will section the beam from A to C. So from A to C. Now what does it mean? It means x is greater or equal to 0 and less or equal to 0.3. So when you cut the beam over this section, so you have to draw the free body diagram. So this is point A, clear, and there will be a uniformly distributed load below this beam, and this distributed load is equal to W, which is equal to 2 kilonewton per meter, and let this distance where we cut the beam is x. So this total length will be equal to x. So when you cut the beam at any section, there will be a shear force V and there will be external moment M, and let this point where you cut the beam is J. Now you will apply the equilibrium condition in order to find this shear force and this external moment. So let's apply. First condition is sum of all forces along y direction is equal to 0 and taking upward force is positive. So you can see there are one force that is acting upward, which is W, and this W is equal to 2, but this is in kilonewton per meter. So when you multiply it with length x, it will be force. So 2 is W and whole length is x. So 2 into x is one force, and the second force is this shear force minus V is equal to 0. So from here you will get this V is equal to 2x and its unit will be equal to kilonewton. Let this is equation number 1. Now we will apply another equilibrium condition, that sum of all moment about point J is equal to 0 and taking the counterclockwise moment as positive. So moment about point J is due to this force, which is 2x, and when you convert this uniformly distributed load into concentrated load, so it will be acting at the mid of this length, and the mid of this length will be equal to x by 2. Clear? So this force, which is W into x, will be acting at a distance of x by 2. This is x by 2. So moment will be W into x by 2, and it is producing clockwise moment, so it will be negative. And there is external moment about point J, which is plus m. Their sum must be equal to 0. So from here you will get this moment is equal to 2 will cancel, and minus x square, when it will move toward right side, it will be equal to x square, and its unit will be equal to kilonewton into meter. Let this is your equation number 2. Now we have find the equation of shear force and bending moment at section 1. Clear? And we will move toward section 2, but before moving towards section 2, you can find the value of shear force and moment at various points of x. So x is equal to 0.3, which is at x is equal to at c minus. Now what does c minus means? That x is equal to 0.3, but it is little before c points. This is c minus. So we are going to find the shear force. So for x is equal to 0.3, put in equation 1. So when you put it in equation 1, 2 into 0.3, V will be equal to 0.6 kilonewton. And you have also put x is equal to 0.3 into equation 2 to get this moment, and this moment will be equal to 0.3 whole square, which will be equal to 0.090 kilonewton into meter, or it will be equal to 90 Newton into meter. So this is the value of shear force and moment at x is equal to 0.3. Now we will move toward another section and we will cut the beam over here. This is section 2 from A to D. Clear? So I will write it from A to D. Now A to D means that x is greater than 0.3 and less than 1.5. 2 meter. So you can see x will be less than 1.2 meter. Clear? So when you cut the beam, so you will have to draw the free body diagram. So this is point A, this is point C, where 1.5 kilonewton load is applied. Uniformly distributed load is acting on the bottom of the beam. This is point A. This distance was 0.3 from A to C. This is 0.3, and let the total length of the beam is x. So when you cut it at this point, there will be a shear force and external moment M, and let this point is J. Clear? So we will apply equilibrium condition that sum of all force along y direction is equal to 0, taking the upward force as positive. Now there are three forces. One is 1.5 kilonewton, the second is W. This force is W, and this W is equal to 2 kilonewton per meter, and the third force is shear force V. Clear? So minus 1.5 plus 2 into this distance x, which will convert it into point load, minus this V, which is acting downward. Their sum must be equal to 0. So from here you will get V is equal to 2x minus 1.5, and the unit will be equal to kilonewton. Let this is equation number 3. Now we will find the moment equation that sum of all moment about point J is equal to 0, taking upward force as taking the counterclockwise moment as positive. So three forces. One is this, which is 2 into x. So 2 into x is force, and it is acting at the mid. So the moment will be equal to 2 into x by 2, and it is producing, because you can see this force will acting at the middle. So this distance will be x by 2, and this force is W into x, which is 2 into x. This is producing clockwise movement, so it will be negative. Another force which is producing movement about point J is 1.5. So 1.5, and the perpendicular distance is totally is x, and this is 0.3. So the remaining distance will be x minus 0.3. So x minus 0.3, and it is producing counterclockwise movement. You can see about point J, so it will be positive, plus external movement, that is counterclockwise. Their sum must be equal to 0. Clear? So when you simplify it for M, so M will be equal to x square minus 1.5x plus 0.45, and the unit will be equal to Newton meter, kilonewton into meter, because we have taken the load in kilo. So kilonewton into meter. Let this equation is equation number 4. Now you can see, you can find the shear force and moment at various length at x is greater than 0 and less or equal to 1.2. So for at x is equal to 0.3, but at C plus, now C plus means that x is slightly away from point C here. Clear? What will be the value of shear force? Because in initial there was no, this was the initial diagram, this, so there was no point load before C. After point C there is a load of 1.5 kilonewton, so due to this shear force will change. So at x is equal to 0.3, put in equation 3 and 4. So if you put in equation 3, you will get shear force which is equal to V, and when you put x is equal to 0.3, so 2 into 0.3 is 0.6 minus 1.5, which is equal to 0.9 minus 0.9, and is 0.9 kilonewton, and moment at x is equal to 0.3 will be equal to, again that will be 90. You can put 90 kilonewton into meter, so you can put and can check it as well. Now what will be the value of shear force and bending moment at x is equal to half of the beam? Total length is 1.5. Total length is 1.5. So at half it will be equal to 0.75. So what will be the value of shear force at x is equal to 0.75. So you had x is equal to 0.5. You have to put it in equation 3 and 4. So when you put it in equation 3, x is equal to 0.75. So it will be 2 into 0.75, which is 1.5 minus 1.5, which is equal to 0. So at x is equal to 0.75, shear force is 0, and moment, when you put x is equal to 0.75 in this equation, so you will get moment is equal to minus 0.1125 kilonewton into meter, or you can say in term of newton it is equal to 112.5 newton into meter. Okay, also you can see that you can also find the shear force at and moment at x is equal to 1.2, because the beam is unsymmetrical. So you can put at x is equal to 1.2 meter. So shear force, again you have to put in equation 3 and 4. So when you put it at x is equal to 1.2, shear force is 0.9 kilonewton, and moment will be equal to 1.2 square minus 1.5 into 1.2 plus 0.45, which will be equal to 90 newton into meter. Okay, so now we will find the shear force at point D, because you can see at point D there is a load of 1.5 kilonewton. Till point D we have a shear force of 0.9, clear, plus 0.9, but at point D there is a load of 1.9. So 0.9 minus 1.5 which will be equal to minus 0.6. So at point D the shear force will reduce from 0.9 to minus 0.6, and when you will draw the shear force and bending you can see that. Okay, so let's move toward drawing the shear force and bending moment diagram at various sections. So I have drawn some portion. So here we will take shear force in kilonewton, clear. So we will first draw the shear force. Let each box vertically, one division is equal to 0.1 kilonewton. Here kilonewton. So at x is equal to 0 we have no shear force, so it will be 0. Clear? At x is equal to 0.3. So you can see, I will show you at x is equal to 0.3. Just before 0.3 we have v is equal to 0.6 kilonewton. So we will plot 0.6. This is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So at this point we have 0.6 kilonewton into meter. At the mid we have shear force is equal to 0. At x is equal to 0.75. So from this point to this point this is 0.75 meter. So at x is equal to, we have at x is equal to 0.5 we have shear force is equal to 0. Clear? Okay, Also we have seen that at x is equal to 0.3, which is c plus, we have b is equal to minus 0.9. So at x is equal to 0.3, but before c negative it was 0.6, but after point c it changed to minus 0.9. So we will plot first minus 0.9. So this is point c. Clear? This is point c. So 1 2 3 4 5 6 7 8 9. So at this point we have minus 0.9. So you can generally draw them. So from 0 to this is 0.6, and from here 0.6 we have 0.9 straight line. This point is 0.9. Clear? And we have seen that at mid of the beam the shear force was 0, so it will be 0. Again at point D, which is at x is equal to 1.2. So at x is equal to 1.2 we have shear force is 0.9. So we will plot them 0.9. This is 0.6, 7, 8, 9. So 9 will be somewhat here. Clear? 6, 7, 8, 9. So it will be here. So I will join this. So 0.9. Okay. Now at D we have 0.9, but at D we have a point load of 1.5. So 0.5 minus 1.5, which is equal to minus 0.6. So at point D shear force will reduce to 0.6. So 1, 2, 3. This will be 0.6. Okay. So we will join it by using vertical line. So this was 0.9 and this is minus 0.6. And again at the end at point B we have shear force will be equal to 0. So this is your shear force diagram for this loading. Now we will move toward the bending moment diagram. So again at point A the bending moment M will be equal to Newton into meter. Clear? So at point A we have bending moment is equal to 0, and at x is equal to 0.3. At x is equal to 0.3 we have a moment of, let me show you, at x is moment is 90 Newton into meter. So let each box is one division here is equal to 30 Newton into meter. So the 90 Newton at x is equal to 0.3. 0.3 will lie somewhat here. So this is 0. This is 90 Newton into meter. As this shear force is increasing, clear, or the slope is positive, so bending and first degree, so the bending moment will be second degree curve in a counterclockwise. Clear? At x is equal to mid, you can see at x is equal to 0.75 we have a moment is equal to 1125. Clear? So we will plot 1125. So at x is equal to, at this mid, this is the mid. So 30, 30, 90, 90 and 100 will be somewhat here. So let this is the point. And again you can see from C to D, this from C to center, so this point, this is increasing, the slope is positive. So again it will be a second degree curve with a counterclockwise. Clear? Now at point D, this is point D. I will show you, this is point D. We have at x is equal to 1.25, we have moment 90. So again 90 is this one and this is point D. and again you can see from center to D the slope is increasing or positive, and the shear force is a first degree line. So the bending moment is second degree curve with counterclockwise. Clear? And now again from this D to B the moment here will be 0, and since the slope is increasing, so again it will be a second degree curve and it will be counterclockwise slope, or the curve will be in counterclockwise. So this is 100, let me check it, this is 112.5 minus 112.5 Newton into meter. This value is minus because you can see this is minus. Now this is our required shear force and bending moment diagram. Let me show you for this beam. Now from this shear force diagram you can see the maximum absolute value of shear force is minus 0.9 or 0.9. So it will be equal to minus 0.9, and that will be equal to maximum absolute value of shear force is 0.9 kilonewton, or that is equal to 900 Newton. This is the absolute value here. And maximum bending moment absolute value is, you can see the maximum value is minus 112.5 Newton into meter, so which is equal to 112.5 Newton into meter. So these are the answers of our question number 5.13. This is the shear force diagram and this is the bending moment diagram. I have tried my best to draw it accurately and as per scale, and you are advised to draw it by yourself using proper scale and you will get the same answer. I hope you have enjoyed the video. If you like it, kindly subscribe my channel and share it within your community. Thank you for watching.